Okay.
A minute or so early, but we'll start. Well, I'd like to introduce to you David Rowe from South Australia. His bio reads, David started crawling towards PowerPoints at 9 months of age. And he hasn't really improved. He's dabbled with real jobs, developing satellite modems, telephony hardware and speech codecs for 25 years. But the pain of corporate life got the better of him, and he went into full-time open source development in 2006. And since then, he's worked on open hardware and software, IPPBXs, the IPO4, developing the world's communications, mesh, potato, echo cancellation, OSLEC, and speech compression, Codec 2 and FreeDV. And he drives a homemade electric car. And for those amateur radio people in here, he is VK5DGR. Over to you, David.
Thank you very much. Thank you very much for all coming to hear this talk. It's one of the highlights of my year to talk here. I'll be talking on open source digital radio. The topics I'll cover, first of all, I'd like to introduce digital radio by comparing and contrasting it to VoIP over Wi-Fi, because you're all probably quite familiar with Wi-Fi, but not so much digital radio, so it's a good starting point for a Linux audience. I'd like to talk about some of the applications for digital radio, and why is it important? Why do we care that digital radio is open source or not? The codec used for the open source digital radio work is a codec I've developed called Codec 2, so I'd like to spend a little bit of time explaining that. Then we'll have a couple of demonstrations. The first will be some stored files that show the difference in what the digital versus analog systems sound like over a typical channel. And then we've got a demonstration of a GUI application that brings all the components together that we've been working on for the last few years. Okay, so just why is two-way digital radio special? The sort of open radio I'm talking about is two-way radio, sort of thing you can do with a walkie-talkie. This is a VHF radio. It operates at around 144 megahertz, and it's a push-to-talk type system. Another example is an SSB type, single sideband type transceiver. This works on the high-frequency radio bands, or HF radio, which is around 3 to 30 megahertz, otherwise known as a shortwave radio. And that's a small portable example. They also come in much larger versions. I'll just plug the antenna back in because we'll need that later. Now, okay, so we want to send digital speech over a radio channel. Why not just use VoIP over a radio channel? So just to illustrate that, I want to compare doing VoIP over Wi-Fi to how digital radio works. So the first really big difference is VoIP over Wi-Fi uses a very large analog bandwidth of around 10 megahertz. Now, that's the width of the spectrum that it requires. Whereas the sort of digital radio systems that I'm working with use only 1100 hertz. So it's several orders of magnitude less analog bandwidth or spectrum that is required, much more compact. VoIP has a typical minimum bit rate of around 1 megabit per second because it's designed for VoIP over Wi-Fi. It's designed for a data channel. We're just putting VoIP on top of that. Whereas the sort of bit rate we're using for digital radio is only 1400 bits per second. So once again, nearly a factor of 1,000 difference. Because VoIP's operating over an IP type channel, it's got a bunch of protocols, one for the Wi-Fi and then various layers of IP, UDP, RDP. That means the protocol efficiency, in particular for voice traffic over VoIP, is very low. The sort of systems I've played with in the past are only around 6% efficient. In contrast, we haven't got many bits to spare or much bandwidth to spare for digital radio. So we've got a very simple frame sync, only using 1 bit out of the payload data, and we get very high protocol efficiencies approaching 100%. Because you've typically got a fair bit of data to play with VoIP over Wi-Fi, you have either no compression or a modest compression scheme like G729, which might be about 8 to 1 on the source data, whereas we're using a Codec 2 at around about 45 to 1 compression. The big difference, of course, is that when you've got a Wi-Fi channel, you've got plenty of data there, so you can send broadband data. In this case, with a bit rate of 1400 bits per second, you won't be sending any real-time video, but you might be able to send a little bit of text or SMS type data along with the voice. So the takeaway from that is that digital radio can be about 1,000 times more bandwidth and power efficient than, say, doing it with VoIP over Wi-Fi. In technical or engineering terms, that's 30 dB. Another way of thinking that is like 1 watt through a digital radio device is equivalent to 1,000 watts of Wi-Fi in terms of its performance. Now the big difference is because of the narrow bandwidth, we can operate digital radio at lower frequencies in the HF and VHF radio bands. Because you're using something like 10 megahertz of analog bandwidth for Wi-Fi, you're really limited to the very high frequency bands, things like the microwave ranges. Now the advantage of operating on HF and VHF is you can go non-line of sight. These sort of radios can go over many tens of kilometres. A HF radio, like the one I showed you a moment ago, can have a global range with no infrastructure. Rather than worrying about Wi-Fi, you really need line of sight to get more than a few tens of metres. And the other big difference is, of course, both systems will do real-time voice, but only the VoIP Wi-Fi system will do broadband data. You can't do broadband data over these systems. They're optimised for voice. Some applications. The one at the moment that I'm having the most to do with is ham radio, which is an experimental service of people, like-minded people like us, very similar to the Linux community. In fact, many people are members of both community. Because it's an experimental service, it's a great way to play with this sort of technology over the air. But other people use two-way radio services and are moving to digital, and that's people like police, fire and emergency services. Another big need for this technology is humanitarian and disaster. When the internet dies, then this sort of thing still works. You can still get your message through. One interesting application is democracy movements, when the internet is actually switched off by someone. You may not have control over it. In that case, you can use this technology to reach out a couple of 100 kilometres, perhaps to a place where the internet is switched on. Use it to bridge that last 100 mile. One interest I've had, and where I've done some work over the last few years, is in the developing world. This technology is also applicable to voice communications in the developing world. At this stage, we're not targeting specific applications, it's more building block type stuff, but there are some real possibilities. One of the key things is the low need for infrastructure. If you're in a village, 100 kilometres away from something, you can use this technology to trunk telephone calls without needing big towers, line of sight, or a fibre optic network. It also has some possibilities for low-cost manufacture and even local manufacture, because as we'll see that in the next talk, the software is moving into the hardware complexity is moving into the software, which brings the cost of the whole system down. Why do we care if digital radio is open source? What's happening out there is that these sort of systems, this is an FM analog radio, they cost about $50, $60. They're transitioning from analog to digital. The last time this sort of technology changed was around 50 years ago. So it does last quite a while. Once you set up a standard, there's a lot of pressure to maintain and continue with that. So the last transition was when we moved to schemes like frequency modulation, FM, and single sideband SSB about 50 years ago. All the other digital radio schemes out there are using proprietary and closed software. In particular, the codecs tend to be closed source. Now, when the power goes out, the cell phone networks die, your 3G data is gone, the internet's gone. This stuff, lives depend on this stuff. So to me, it's really, really important that we have an open source alternative out there when it comes to using things like emergency services. And the way these standards work will be locked in for many years unless we act and develop open systems now. There's some technical reasons why we want it to be open. The ability to innovate and experiment, make these systems better. There's technical reasons. If you know what's inside the codec and it's not just a black box, you can combine that in clever ways with the modem to improve the overall system performance. If it's a black box and you're locked out, you just have to treat it as a bit stream and hope you can do your best. We're showing some technical superiority already. Our codec's running at a fraction of the bit rate of the closed source competitors, and that allows more channels, more efficient power usage. When it's the closed source form that this software tends to come with is locked into chips that you put inside the radio, or at best licensed software. Now you can't use that to move to different platforms or do interesting new experimental services. However, when it is just software and it's open software, we've already seen this rapid porting to different platforms. Most of my work's done on an x86 laptop, this one here, but the software we've developed has moved to Windows, BSD, Mac. People are playing with it on Raspberry Pis. I'm particularly interested in doing some single chip DSP implementations, and people have got it running in Android. And you'll see an Android implementation of this technology in the next talk by Joel Stanley. Radios 20, 30 years ago used to be big boxes full of transistors and even valves. Now what they're turning into is software. Software can be free, which can make communications free. And it can be free as both in speech and as in beer, because the complexity moves inside the hardware. That means the complexity moves in software, means the hardware becomes much simpler and therefore cheaper. I'd just like to talk, I guess, on a personal level about why this matters to me. I've got some skills in speech coding and a bit of a background, less of a background, but I know something about modems and radio. And it means a lot to me to use them to improve the world a little bit, to develop these things, throw them out into the world and hopefully help people out. It's also a fun problem. It engages me at pretty much the limits of my technical abilities. So it engages me, keeps me absorbed solving the problem. And I get a lot of encouragement from other people like you guys who want to see these problems solved. Also, I really like working with the open source community and like-minded people in the ham radio community. It's guys like you that make me want to get up in the morning and work on this stuff. So thank you very much. And I also like talking to people about it at conferences like this. Okay, so this is a typical digital radio system. First thing is we have some analog speech that's sampled by a microphone, and that enters the speech codec, in this case a codec 2 encoder, where it gets compressed down to a low bit rate, something like 1400 bits per second. It then goes into a modulator. Now that takes the bits and converts them into a series of audio tones that can be then sent through some sort of analog radio system and over an analog radio channel. That channel's never perfect. You'll get noise added. You might have some little tuning errors, so the frequency will be a little bit offset from where you want it. And then that will get received by a radio at the other end. And then those audio tones will go through a demodulator and get converted back into a bit stream. It's a little bit like the old analog telephone modems we used to connect to the internet, but in this case over a radio channel. And then we have the codec 2 decoder, which converts the bit stream back into audio samples, which can be played out of a speaker. Now, I've got an explanation of how codec 2 works. For those who came last year, this is a little bit different. I keep working on different ways on how to explain it. It's fairly complex DSP technology inside the code, but some of the principles are quite easy to explain. Okay, this is a little chunk of sampled speech from a female speaker. She's saying the word "these," and this is along the bottom here. We have a time axis. This is in samples. This is around 40 milliseconds of speech from a female speaker. Now, one thing you can notice is that the signal it's evolving slowly across the time, but it does tend to repeat itself. And as you'll see in a moment, anything that repeats itself in the time will also repeat itself in the frequency domain. So this is the spectrum, or a graph of the frequency response of that signal. Along the bottom axis, we have frequency from 0 to 4000 hertz, and along the side here it's the amplitude in dB. But basically the higher it is, the stronger the signal is at that particular frequency. Now, as we saw before, the signal repeated itself in the time domain. It turns out that anything that repeats itself in its time domain also repeats itself in the frequency domain. So you can see this repetition across here. In this case it's a bunch of spikes that repeat themselves at regular intervals across the spectrum. We call these spikes harmonics, because they're harmonics of the pitch of the person. And the difference between the spikes, or the difference from the start of the spectrum at DC here, is the pitch. And this particular speaker is around about 300 hertz is the pitch of their voice at this particular point in time. Now, one way we can reduce, the goal of speech coding is to reduce the amount of information we send to the other end. We want to throw away as much as we can, but still retain enough information so that the speech signal can be understood when we decode it. So one way we can throw away some information is that if we know the pitch of the speaker, we really don't need to know the frequency of each of these. We just know to repeat a line every, say, 300 hertz in this case. And then we've got enough information to specify where all these lines should be. So that's one thing we do. We estimate the pitch and transmit that to the other end. It turns out the other thing that's really important for speech perception is where the peaks in the spectrum are. So we have a bit of a peak around here, and we have another one around here. And it turns out that the ear listens for where those peaks are, and that's how we understand what's being said. So the other piece of information that's really important is just the height of all these peaks, or the amplitudes. So we can extract those as a sample, one sample for each of the harmonics of the speech, and then we can really pretty much throw everything else away, and that's what we're left with. So the amplitude of each harmonic and the spacing between them, which is the pitch. Now, that information evolves over time as the person articulates the words. So as we move forward in time, you can see it slowly varying. So we're just stepping forward in time, and they'll step back. Every 40 milliseconds you see it slowly evolving. So because it's evolving, we have to update those amplitude samples of the decoder, so we tend to retransmit a bunch of samples at regular intervals, say every 40 milliseconds. And that's pretty much how codec 2 works. Okay, so remembering we had the amplitudes there, that was a lot of that information across the top there. This is the bit allocation for the speech codec, or how many bits we apply to each parameter. So those amplitudes are where the bulk of the bit rate goes. That's around 36 bits for every 40 millisecond frame. We also transmit the pitch information, which, as I said, was the spacing between those harmonics. And that's combined with the energy at around about 16 bits per frame. You can think of the energy as the volume at that point in time. As the volume goes up and down, as we articulate words, then the energy will change as well. There's another parameter I didn't discuss, and that's called voicing. That's really whether the sound we're generating is a consonant or a vowel. When it's a consonant, it's mainly noise-like, sh, and we don't need that pitch information. We just put random noise in there instead and shape that with the amplitudes. So the voicing is a little binary switch that we update regularly as well. Total of 56 bits per 40 millisecond frame, or 1400 bits per second. So now I'd like to demonstrate analog versus digital radio system. So what we're going to do here is the whole system. We'll start with some input speech, and we'll pass it through the codec, and then through the modulator, and I'll play to you what the samples sound like from the modulator, the modem tones. Then it passes through a HF VHF radio. In this case it's a simulation where I've added some noise and a frequency shift to simulate what happens when we go through a radio channel. Then we'll demodulate the signal and listen to the output. Now, the problem is that as we add a bit of noise, we get bit errors on the received signal, and that means there'll be some distortions in the digital data. To compare the system to the analog one, I'll also have a demonstration that pretty much bypasses these blocks, but just takes the microphone signal, passes it through the radio, then plays it out the speaker. So I'll play a simulation of the analog system as well. Now, the first thing we do is, in this system is generally the input speech is filtered between, say, 300 and 2600 hertz. That's just so we concentrate most of the power in the parts of the speech that matter. Okay, so this is the input speech.
W5ABC here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo. I'm located in Sackville, New Brunswick.
And this is what the modem tones sound like. I'll just play this for a moment because it's a bit loud. So that's what we send over the air. Now when that gets received at the other end, there's noise and frequency offsets, and it sounds a little like this. So buried in there somewhere was that original modem tone. Then when we decode it, we hear something like this.
W5ABC here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo. I'm located in Sackville, New Brunswick. Okay,
so you can probably hear in there a few points where the voice stuttered and made strange sounds. We had quite a lot of noise there. That was a signal to noise ratio of 5 dB. And the bit error rate was 1 to 2%, so quite a few bit errors were in there. And yet it was still quite intelligible. You could work around those problems and understand what was being said. Now, I'll play what it sounds like through the analog system, so just taking that exact same channel, signal to noise ratio of 5 dB, and what the analog system would sound like.
My name is Bruce, Bravo Romeo Uniform Charlie Echo. I'm located in Sackville, New Brunswick.
So you can hear that the main thing in there is a hell of a lot of background noise, and every now and again the speech signal pokes above that noise. That's really characteristic of digital versus analog systems. With digital you get that full quieting, whereas with the analog you've got to put up with the background noise. So I'll just compare those two again. This is the digital.
W5ABC here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo. I'm located in Sackville, New Brunswick.
And the analog. Okay, so now in an ideal case where we had a very high signal to noise ratio, this is what the digital would sound like with no errors at all.
W5ABC here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo. I'm located in Sackville, New Brunswick.
And this was the original for comparison.
W5ABC here is Victor Echo 9 Quebec Romeo Papa. My name is Bruce, Bravo Romeo Uniform Charlie Echo. I'm located in Sackville, New Brunswick.
Okay, so that's basically the difference between coding at 1400 bits per second and original, but with no bit errors. I've been working on this technology for a couple of years now, and some of you may have come to previous presentations. So I just wanted to give you a little bit of an update of where I'm at and with the team of people that I've been working with. Early last year I had the codec, but we wanted to get it on the air, so we needed the modem. So I spent several months rewriting a modem for HF radio. There was a modem designed for this sort of system several years ago. Unfortunately, it was closed source, and when the author stopped working on it, the source was not available, and that was lost to us. So I made sure that when I rewrote it, it was GPL, and it's been released, and it won't be lost again. As I wrote the modem, I also learned quite a few things, so I did some work on blogging that and explaining how it worked, as much for my own benefit as other people. I think that's one of the benefits of open source. I also played around with some higher bit rate modes of codec 2. We tried bringing it up to 3200 bits per second. It doesn't sound all that much better than the 1400 bits per second, unfortunately. So I think we've found the sweet spot at the low bit rate, but one day I might try that again. I also worked on something called a post filter, which improves the quality quite a bit at all bit rates. How the post filter works is it takes the output speech from the decoder, then applies some DSP filtering techniques to improve the quality a little bit. Because it just works on the output speech, it doesn't require any additional bits. So most importantly, it still runs at the original bit rates that we used. Now the major project for the last several months of last year was working with a team to develop a GUI application called FreeDV. That was started by a gentleman by the name of Dave Witten, who lives in the US, a ham radio operator. He did the design of the GUI and the various architectural components, and then I helped him out with the integration, and together we released it in December. So what FreeDV is a cross-platform GUI application that will allow anyone to hook up to a radio and start using this stuff over the air. It encapsulates all the modules we've been working on. We'll have a demonstration of that in a little while. Where I'm going with this work, the blue boxes sort of indicate where we've gone the last year or two. We've completed the 1400 bits per second codec. We wrote the modem and we integrated it in a GUI called FreeDV. Where I'd like to go in the future is do some more work on making the system more robust over HF radio channels. The channel I played to you was sort of a best case. There are some other HF radio channels where the system doesn't work as well as the analog, and I need to do some work to improve that, probably involving some forward error correction and some other techniques to improve the quality when there's bit errors. Most of the work to date over the air has been for HF radio, the 3 to 30 megahertz, which is shortwave radio. The other area we'd like to work on is VHF radio for this sort of device, two-way radio, handhelds. So we need to do some more work. You require a different modem to operate often VHF bands than to the HF, so that involves integrating with a new modem. I'm also very interested in embedded work and have a bit of a background in embedded and open hardware. So what I'd like to do is take the codec and modem software and see if I can get it down to a single chip. A lot of people are interested in doing that on things like Raspberry Pis. I'd like to go a step further and put it on a big microcontroller, something that doesn't have much of an operating system at all. Once we get it down onto a single chip, we can start thinking about integrating it in existing radios at a hardware level, and you no longer need a laptop to run the mode. And the next presentation, after lunch by Joel Stanley, will show you the software running on an Android device, just showing with a very simple radio. Okay, so FreeDV is a cross-platform application. We wrote it for Linux and Windows. A lot of people out there who do radio work, like ham radio operators, are sort of Windows-centric. We're slowly converting them to Linux, but we really did need a Windows application. So we put a lot of effort into making it cross-platform as we developed, using libraries such as WX Widgets and Port Audio. As soon as we released it, some people started porting it to Mac and BSD, and we've got some initial code running there as well. It's all GPL version 2.1, the only open source digital application that we know of, and it allows any SSB radio to be used for digital voice. It's been set up, there's been quite a lot of experience over the past few years of ham radios operators working with this sort of software. We've incorporated that experience to make it easy to use, and it's kind of fun. It's got some neat GUIs and things to play with. So I'll see if we can get that going now. What I'm going to do is do the receive side here. So I'll take a signal off air using a very simple antenna, a piece of wire. Receive it on my HF radio here, and then do the FreeDV decoding on the laptop. The signal is being transmitted by Mark Jessup, sitting up the back there. He's got another example of a HF radio, which is a large man pack. Those in front of him, if you're getting a little warm, just don't worry too much about that, okay?
100 years.
There it is.
That is exactly what was happening with digital voice. But now, hands are in control of technology again. FreeDV is unique as it uses 100% open source software, including the audio codec. No secrets, nothing proprietary. FreeDV represents the path of the 21st century amateur radio, where hands are free to experiment and innovate, rather than a future locked into a single manufacturer's closed technology.
So I'll just turn that down while I explain what's going on. So Mark's transmitting over there, I'm receiving. What we've got up here is called a spectrogram, and that's just showing a time plot, rolling plot of the spectrum of the received signal. What's actually coming in off the air, that's the spectrum there of the modem signal. That's what we call a parallel tone modem. There's actually about 14 carriers that we're receiving there, and then demodulating. The centre big spike in the middle is some synchronisation information. And when we plot that signal over time, you get this sort of waterfall or spectrogram display, which is sometimes a little bit more useful in tuning in. It also has some other plots, such as this is what's called a scatter plot. That just gives us an indication of quality of the modem signal. The smaller those dots are, those little clouds of points, the higher quality of the signal. When there's more noise, those dots get bigger. It also has various displays, like oscilloscope type displays. That's the raw signal coming out of the radio. You can use that to adjust the levels. And down the bottom there, you can see some very low rate text information coming through with Mark's call sign at the bottom there. And that might be the radio you're using, is it, Mark? The other number? Yeah. Your home locator. Okay. So if Mark was transmitting from a long way away, that would give us sort of like coordinates of where he is. Okay, so that sort of completes my talk, and happy to open it up to questions from there.
So you're Stephen Boyd. I used to be VK2DNN, but I should get my licence back again.
Sure.
So you're using analog to analog, then going out over SSB. Can we reduce a lot of the complexity and improve the quality of the signal by just skipping all that and putting the codec on a straight digital radio? Is there anyone trying to do that? And I mean, I can see why you do SSB, because there's a huge amount of installed base out there.
That's right,
but
yeah.
They're getting the kit for just the pure hardware. What sort of cost and time and thing is to get that sort of stuff happening? Any idea?
Yeah, well, there are people who sort of do the whole thing in software when they have software-defined radios, and so they can just go directly to RF, basically, out of the software-defined radio. That happens at various levels. You can get software-defined radio that operate under Windows or Linux, so it's just like another program in your background. Then you have a box that's your sort of power amplifier. It turns out, though, this scheme is fairly benign in terms of the signal. The SSB radio is just acting like a big up converter, moving the signal up to RF frequencies, and it doesn't tend, as long as you get the levels right, it doesn't tend to mess it up too much. And as you say, it lets us use the installed base. But yeah, there are some people who are interested in doing this directly, and that's probably how it's going to go in the future. You'll have it all integrated in the one box, or in software with a small ancillary box that does the RF side.
Hi there, Laurie Brown, 1KLB.
Hello.
You mentioned the low rate data. I was just wondering how that fits in. Do you actually have a tagging on the frame form, or and where's it slot in it, and at what sort of rate?
Yeah, it's a good question. Because this is an example of, because we've got control of the speech codec, we can do things that you wouldn't normally be able to do. I steal a bit every now and again from the speech codec. One of those voicing bits I take away at the encoder, and then at the decoder I use an algorithm to reconstruct that voicing bit, knowing the values of adjacent voicing bits. And it turns out you can't really hear the difference. So we steal 1 bit per frame. It's 25 bits per second, that auxiliary, or 50 bits per second, I'm sorry, that auxiliary data bit. Yes. Hello.
How low do you think you can go with something like an AVR, or will you need something more powerful like an ARM processor or something like that?
Yes, looking like high-end 32-bit microcontrollers. I think we should be able to get it running on that. And because it's open source and we know a bit about the algorithms, there's quite a lot that can be done to get the complexity and things like memory consumption down. That's pretty critical on some of the low devices. So typically you're going to need probably a couple of hundred MIPS and a couple of hundred K words of memory to make it run once it's fully optimized. Yes. Yes.
Hi David, Andrew Tridgell. I work on firmwares for telemetry radios, so some similar stuff. I'm interested, this is still push to talk basically. Have you thought about integrating sort of time division multiplexing type algorithms to allow both ends to transmit at once and synchronise their clocks appropriately? Yeah,
in fact that's something I've put in a few project proposals about, and it's something I'd really like to work on. There is some work going on with two-way radio with single channel repeaters where they have 2-slot TDMA, one receive, one transmit. But you can open source TDM something code. Cool. Yep. Yeah. The next step to that is to add 4-channel, and then you can have full duplex over repeaters. So that is something that would be interesting to try. Yeah. And would also enable the other application I have in mind for that is the developing world telephony, where you want to trunk telephone calls. So full duplex will make it much more like a real telephone call than a two-way radio experience.
I'm not sure if this is a worthwhile question, but you said about voicing, and that's basically consonants and vowels. For languages with like different sort of sounds and how that like, does this need to be optimized or changed for like different kind of voicings that are?
It tends to work fairly well across most languages.
Yeah, okay.
Yeah.
Thank you.
Do you have any example of music or some non-speech audio content going through this codec?
Yeah, you don't want to hear it.
It would be interesting though. Artifacts are always interesting.
Yeah, to get to these low bit rates, we have to make a lot of assumptions about the nature of the signal, and we really assume it's human speech. So when you put other signals through, it tends to break down pretty badly. You hear something, but it's pretty funny. Hey, it's open source. You're welcome to try and download it and compress whatever you like with it. Yeah.
One of the more bizarre things we saw yesterday in the multimedia session was using a dynamic array of ASCII characters, building up video out of ASCII characters on a text type terminal. Presumably the data transmission rates of that are pretty low. What does it take to transmit data, and would that be another way of getting a whole lot of the processing done at the receiving end?
Yeah, there are some applications already for HF radio for sending images, like slow scan television, or just small images sent fairly rarely. And they use pretty much the full channel, something like 2.5 kilohertz of analog bandwidth and a bit of a higher bit rate, and things like forward error correction to make sure the image goes through okay. And you can download software. I don't know if it's open source, but there certainly is free software that you can download to do that. It uses very similar modems to the sort we're working on. The difference is for things like that, and for broadcast, it's one way. So you can have a lot of delay in the signal. It doesn't matter if you buffer it over a second, put lots of forward error correction on it. As long as you can reconstruct it at the end, it's okay. We had to make certain design decisions to make sure it could respond very quickly in a push to talk. For example, the modem has to lock up very quickly, and if it loses acquisition, it has to reacquire very quickly. So the modem and channel link design is a little bit different for real-time two-way speech as compared to, say, just sending an image or even just broadcasting. Yes?
Your codec 2 uses a lot of assumptions about the audio to strip out a lot of data. Can you use it to actually clean up a signal?
Only a little. What I do have some algorithms for is if the input signal goes in as noisy, then it can suppress some of that background noise. Yeah, but typically you'd use a noise suppressor algorithm to do that. And Speaks, another open source speech codec, that has a nice little noise suppressor that's available. It's open source and GPL if you wanted to do that ahead of time. Yeah.
I guess just further on that, what about a feedback loop with the codec, obviously comparing the actual real-time input and the codec output to, I guess, keep cleaning that up, I guess a closed loop effectively before the final encoding?
Yeah, the issue with that is delay. You can sometimes do those sort of loops, but it tends to add processing delay and coding delay, and latency is an issue for real-time communication. That you can use those sort of feedback loops, though, in some part of the system. For example, in cleaning up the modem signal.
How low can you actually drive the output power to still get like a really good quality signal, say powering it off 1.5 volt batteries?
Well, it really comes down to the amount of power you need to get over the link. Typically people run this sort of stuff in the 5 to 20 watts range of transmitted power, but that gets you interstate, 1,500 kilometre type distance. But you can wind it right down if you just want to transmit across the room like we did, or across the campus. It just comes down to signal to noise ratio at the receiver. So there's no real limits on supply voltages if you've got the hardware that'll give you a link at a decent signal to noise ratio. Yes?
You've mentioned the other codecs, but without actually giving some comparisons. How do you feel you relate to the rest of the codecs out there, and what are your chances of actually getting this out in some of the commercial radios into, say, the emergency service or what have you? Is this realistic, or is this going to be stuck just with us playing with it?
Really good question. I don't have a good answer for that. My interest is in building the technology building blocks and getting it out there and making sure it works really well. From then on, I don't really know. I haven't got a lot of stomach myself for the politics or writing standards or even to build this thing into a real product is a lot of work. Yeah, but good question. I think having the alternative out there will make me feel a lot better though. And I'm certain people like the hams are going to pick this stuff up. A lot of those are involved in emergency services. They're often the last point of call when everything else fails, and they've all approached me and they're all interested in experimenting with it already.
So obviously, David, you know who I am, VK3 XJM. We've done a bit of mucking around with Codec 2. I just wanted to make a comment about the question before that was asked about the output power. Last night, myself and Mark were down on the bank of the river, and we were mucking around with Codec 2. I was using an FT817, Mark was using his Codan. I was running the FT817 at 5 watts, and I was getting 100% copy into, I think, was it Newcastle? Into Newcastle, and I was also receiving the station in Newcastle with 100% copy. So I haven't tried to run it at any lower output powers than that, but it's all about getting above the noise floor at the other end. There needs
so that's
to be
roughly 500-600 kilometres from here.
Yeah.
With a bit of wire strung over the creek. Try doing that with your Wi-Fi.
Yeah, quite literally. Yeah, quite literally, a piece of wire strung over the creek and an earth clamp on a galvanised pipe that went into the ground. So, very, very basic antenna setup.
Just a question more out of ignorance. Is the digital signal processing built into some of these HF sets like the 817 have any effect on what you do?
Yes, it can do. If you switch on some of the clever noise suppressors, it'll kill it.
More questions?
It's kind of a related question. What about some of these microphones with the speech compressors in them? Does that kill it as well?
Yeah, the modem sort of likes to see a very linear channel, so you'd want to bypass all that and just treat the radio as an up converter for the signal and a down converter.
How does the quality compare with the proprietary codecs that are running at twice the bitrate?
That's a really subjective question. A lot of the hams are enthusiastic about it, say this is better, but I haven't heard much from the other side. So I think the best I can say is they're roughly comparable. You'll have the similar sort of complaints about both of them, and you'll get some people preferring one, some people preferring the other, and You have a few religious wars, but ultimately it'll be, fairly similar. It's what we call communications quality speech. So it's the sort of, crackly two-way radio quality that you get out of one of these. Maybe a step beneath what you use. What's being said, or enough to get the message through, and recognisability. You've got a reasonable idea if it's your friend or someone else on the other end of the line. Yeah. And a level above the robotic sound, where it just sounds like a speech synthesizer. That's not MP3 quality or anything like that. One up the back.
All right. Well,
there's one more question up the back.
Sorry.
Yep.
Where are you?
Sorry.
How do you differ from something like Speaks or ILBC?
The bit rate. Speaks, the lowest bit rate you can really do realistically with that is around a bit under 5,000 bits per second. After that, the quality of this codec takes over and we go much lower. Also, Speaks isn't really optimised for digital radio channels. It's more sensitive to bit errors, which are more prevalent on radio channels. Yeah, so between Speaks and now Opus at the high end and Codec 2 at the low end, we pretty much have, two-way radio quality speech right up to professional recording quality covered with open source software.
So on the analog side of the before you encoder, is there any? Because I assume the first thing you do when you get it is clip everything above 3,000 hertz and
yes,
everything below. So if you were to filter before then, how is it affected by audio compression?
You wouldn't want to do any compression there, but what is sometimes useful is equalisation.
Yeah.
We found a big difference in speech quality. Some microphones, especially PC-based headsets, have a lot of bass to them, and that's not very useful. So we've actually got a built-in equaliser in the like a graphic equaliser, 3-band parametric equaliser that you can set the high, low, and the mid-range. And there's a YouTube demo off the FreeDV site that shows how to adjust that. I like to make my presentations a little bit shorter because I like to hear the feedback from you guys, but it's hard on now. Can't help it here.
So everything you've talked about and demonstrated, I'm assuming assumes a ham license, right? To get access to those frequencies.
To transmit on these frequencies, you need a ham license.
Yeah. So is there any applicability to any unlicensed frequencies and equipment that you could use in that? I mean, I'm assuming shorter range, but.
Yeah, you can. There are some ISM bands in the VHF range, I believe, that you could use to experiment with this stuff without a license. Yeah, but a ham license also isn't that hard to get, and a lot of people will help you out and do that. And the communities are great; they're fantastic, a lot like the open source community. So, I'd encourage any of you who are interested to go ahead and have a go at getting a ham license. It can be done in a weekend course. Have a play with the equipment. And
yeah, have a play with the equipment. We'll show you what you need to know.
Well, there's 10 minutes to go, but if we've run out of questions, we'll call it quits. So, no more? All right, well. That was an absolutely brilliant talk. Thank you very much, David.
Thank you.
And to keep the project warm, a blanket for you.
Thank you very much.